So far, when we're talking about the speed of a reaction, the only way to determine the rate law is by looking at experimental data, because I told you you cannot look at the stoichiometry of a reaction to determine the rate law. Well, what we're going to do now is actually look in detail at what's behind one single reaction and realize that we actually can determine a rate law if we look into the details of a specific reaction. So the first thing we need to talk about is a reaction mechanism. So the reaction mechanism is the detailed steps that occur as the reactants are turned into products. So when you see one single reaction with reactants and products, that's not all that's going on. There's a lot of behind-the-scenes action that's happening. You rarely will see reactants and products, and that's the only thing that was involved in the reaction. Instead, reactants will be transformed into intermediates, which are then eventually going to be turned back into products. So there are a number of steps that occur. Elementary reactions are each single step in a reaction mechanism. So if you have 3 different elementary reactions, those can add up to your final reaction, and we'll see that in detail in just a couple of seconds. The last term that we need to go over is molecularity. Now, molecularity is the number of molecules that participate as reactants in an elementary reaction. So let's look at this example. You have unimolecular, meaning one molecule. So if you look here, the only way to have a unimolecular elementary reaction is if you just have one single reactant. It can be bimolecular, meaning you have 2 molecules, 2 of the same molecule, or it can be bimolecular if you have 2 different molecules. It can be termolecular if you have 3 of the same molecule. It can be termolecular if you have 2 of one molecule and 1 of a different one, or you can have 3 different molecules and it still be termolecular, meaning 3. You don't go above ter. So let's look at how to actually combine these elementary steps in order to get your overall reaction, and then look at a couple of terms. So if I were to add these 2 elementary steps to get the overall reaction, I would notice that I've got 2 NO2s for my reactants. So I'm going to have 2 NO2s and a nitrate, NO3, and a carbon monoxide, and that would produce nitrogen monoxide, NO, plus NO3, plus NO2, plus CO2. So I've already combined them. Now, the one thing you do have to do once you add 2 elementary reactions together is you have to simplify. So the first thing that I can do to simplify this, if you notice I've got NO3 on my reactant side and NO3 on my product side. And so I'm going to cancel out those NO3s. The other thing is that I have 2 NO2s on my reactant side and 1 NO on my product side. So I can simplify that. If I've got 2 NO2s on my reactant side and 1 on my product side, I can simply get rid of the one on my product side and make the 2 NO2s into just 1 NO2. Okay, so I'm going to have just NO2 now because the 2 NO2s became just 1 since I simplified. Carbon monoxide producing nitrogen monoxide and carbon dioxide. And so that is my overall reaction there. All right, so let's talk about a couple of quick terms that I can use when I'm talking about my elementary steps and my overall reaction. So the first thing I wanted to talk about was your intermediate. Okay, so your intermediate, if you notice on this graph, your intermediate exists right after that transition state at the bottom of that hump in the middle. Okay, and so what your intermediate is it's a substance that's going to be formed and consumed over the course of the reaction. So if you notice, look at step 1. Over the course of step 1, your NO2s react together to produce NO and NO3. Then that NO3 is used up in step 2 in order to produce NO2 and CO2. So NO3 is going to be an intermediate, all right? Now, if you notice on that graph, the other thing that you have is your transition state. Okay? We will never be working with the transition state. I just want you to be aware of what it is. And the reason why we never work with it is because it's an unstable form of that substance. During that state, bonds are going to be being broken and then formed. And the reason why we never work with the substances in the transition state is because they're so high in energy that they are not going to last long enough for us to be able to isolate them, whereas we can isolate an intermediate if we need to. I wanted to note one last thing about this graph that you see. Notice this is going to be a 2-step graph, and you know it's a 2-step graph
this is going to be a two-step reaction, as we saw, step 1 and step 2, because it has two humps. You got the first transition state to an intermediate, and then another transition state to your product. So I know this is a two-step reaction. One question that I could be asked of you is, which is the slow step? Meaning you're going to have one step that's a slow step and one step that is a fast step. And I'm about to talk about that and the significance of that. But the important thing for you to note is by looking at a graph, you can actually determine what the slow step and the fast step are. The slow step is going to be the one with the higher activation energy. So if you notice, this first reaction has a higher activation energy than the second reaction. The second reaction's activation energy is very, very small comparatively. And therefore, you know that the first step is going to be your slow step, or as we call it, your rate determining step, which I'm about to talk about. Now, the reason why we've been talking about elementary steps, because the question is, well, if we just take elementary steps and add them together, why are we even looking at them? Why do we care? Well, the cool thing is we can actually use our elementary step in order to determine our rate law. So a rate law of an elementary reaction is based on its molecularity. Specifically, what that means is that the rate law for an elementary reaction can be written by using its coefficients. Better stated, we can use the reaction's stoichiometry. So whereas we cannot use the stoichiometry for an overall reaction, we can use the stoichiometry of an elementary reaction in order to determine the rate law. So if you have the elementary steps, you can determine the rate law, which is great. Otherwise, if you're just given the overall reaction, as was stated in the previous lessons, we have to determine the rate law experimentally, like we did using the graphs, and then also by analyzing changes in concentration. Okay, so how exactly do we determine the rate law using an elementary step? Well, let me show you an example. So if I have a multi-step reaction, right, which consists of at least two different elementary steps, there are two different ways of determining the rate law. The first one is if your first step is the slow step, or what we call the rate determining step. So let's look at this example. So here, I give you two different elementary steps. Hydrogen reacts with ICl to produce HI and HCl. That's the first step. And then HI plus ICl produces I2 and HCl. So the first thing it asks you to do is to write the balanced equation. So this is a review from what we just did. So we're going to combine these together. So we've got H2 plus 2 ICLs plus an HI, and that produces an HI, 2 HCLs, because I combined the HCLs together, and I2. Now, anything in common on both sides? Well, I have an HI on my reactant and my product side, so those are actually just going to cancel out, and so what you get is H2 plus 2 ICL produces 2 HCl and I2. An intermediate, well, HI is your intermediate. And you know it's your intermediate because it was produced during the first step and it was used up during the second step of your elementary steps. Okay? For C, it says if the first step is the slow step, which it has to be, the first step has to be the slow step for what we're about to do, and the second one is the fast one, what is the rate law for the overall reaction? So as I had just stated, if you have your elementary steps and your first step is your slow step or your rate determining step, because your slow step determines the rate of the overall reaction, then you can simply use the stoichiometry of your rate determining step. So my rate determining step is my first step. H2 plus ICl produces HI plus HCl. So all I have to do is simply say, okay, my rate law equals K times the concentration of H2 times the concentration of ICl. Notice there are not going to be any exponents. It's first order for both H2 and ICL. And the way that I know that is because that is the stoichiometry for that slow step. If the stoichiometry for the slow step were 2H2 plus ICl, then my rate law would have been K times the concentration of H2 squared times the concentration of ICl. So if you know your elementary steps, and you know that your first step is your rate determining step or your slow step, this is really easy. You just use your stoichiometry. Please keep in mind that you cannot do this unless you have your elementary steps and the first step is the slow step. If you're given the overall reaction, you have to use experimental data in order to determine the rate law.
Now, the last thing that I'm going to go over in this lesson is catalysts. Now, a catalyst is a substance that changes the speed of a chemical reaction without undergoing a permanent chemical change itself. And the way that they do that, catalysts lower the activation energy for a reaction by providing a different mechanism for the reaction. So as you can see in this graph, the red represents an uncatalyzed reaction. And so what a catalyst does is it provides another way for a reaction to occur. And ultimately, by providing another mechanism, it lowers the activation energy. By lowering the activation energy, which is ultimately what dictates the speed of a reaction, it actually speeds up a reaction. And so in order to identify a catalyst, you simply have to keep in mind that it's going to exist as a reactant and it's going to exist as a product as well.
So whereas an intermediate is going to be produced and then used up during a reaction, you know something is a substance is a catalyst if it exists at the beginning of the reaction and at the end completely unchanged.